In this video, I'm going to show you how to prove the Casimir effect, how to derive it. In particular, Casimir considered the space between a pair of conducting metal plates, which are placed at a distance a apart from each other. So you should imagine the two plates, and these are two-dimensional plates. For example, we can think of them parallel to the xy plane, and the distance between them is a. Now, if we consider stationary waves, for stationary waves, the transverse component of the electric field and the normal component of the magnetic field must vanish on the surface of these conductors. Why is that? Because the charges should be free to move on these metal plates, right? And therefore, if there is an electric field on these plates, or also a magnetic field, then the charges would be constrained by a force. But this should not be the case if these are perfect conductors. And assuming the plates lie parallel to the xy plane, the standing waves can be written in a simple form. So psi sub n, and then I will explain a little bit more what psi sub n is, of x, y, z, and t, we can write it in this form: e to the minus I omega n t e to the I kx x plus I ky y times the sine of kn z, where kn is simply n pi over a. N is an integer, a is the distance between the two plates, and psi stands for the electric component of the electromagnetic field. This form here satisfies the wave equation that can be derived from Maxwell's equations, and there is the sign here because this function must vanish at z equal to 0 or z equal to a. So remember that this is the z direction here because the plates are parallel to the xy plane. So this is important. And from Maxwell's equations, or from the wave equation, one can derive a relationship between omega n and kx, ky, and kn. In particular, one can find omega sub n equal to c, speed of light, times the square root of kx squared plus ky squared plus n squared pi squared over a squared. And you can check that with these conditions, we have that psi sub n satisfies the wave equation. Now, what we want to find is the vacuum energy. And the vacuum energy can be obtained as a sum over all possible excitation modes. We will consider the area of the plates to be large, and we will call the area A, which is equal to L sub x times L sub y. So these are the dimensions along x and along y, because the plates are thought to be parallel to the xy plane. How do we find the vacuum energy, the energy of the vacuum, which I will call E with these two angular brackets? So we are going to sum over all the possible quanta that we have. So we have h bar times omega sub n, and omega sub n is constrained by this equation. So we have to sum over all the possible values of n from 1 to infinity. We are going to start at 1 here simply because, well, in principle you can start at 0, at n equal to 0, but you can see that if you set n equal to 0, you get kn equal to 0, and therefore the sign will be 0 and psi 0 will be 0. So that would not be an interesting function. Psi equal to 0, that's a trivial result. We are going to consider the non-zero waves. So we are going to start at n equal to 1, and then it's not over. So this is not the energy, because we still need to integrate over all the possible values that kx and ky can assume. So we have to integrate over dkx and dky, and we also have to multiply by the area of the plates, and I will try to motivate this kind of thing. And we have to divide by 2 pi and 2 pi here to make this a little bit more consistent. Why is that? Well, the area is of course proportional to length squared. So this is length squared. So let's try to check the units first. Whereas these quantities, kx and ky, which are the wave numbers, are length to the minus 1. This is length to the minus 1. So length to the minus 1 times length to the minus 1 times length squared will give you something that has no unit. And since this is energy, of course, we get energy. So the dimensions are correct. But let's try to motivate also these factors of 2 pi. And why do we have to integrate and multiply by the area? Well, in general, as I said earlier, we are going to assume that the area is large enough so that we can consider the dimensions of the plate to be infinite. So it's as if Lx and Ly go to infinity. And Lx is related to Kx because Lx can be written as 2 pi divided by the change in Kx. And similarly for Ly. So it means that Lx Ly, which is the area, can be written as 2 pi squared divided by delta Kx delta Ky, or if you want 1 over Lx Ly is equal to delta Kx delta Ky over 2 pi squared. And when Lx and Ly go to infinity, from Fourier analysis, it is possible to show that these changes will become infinitesimal, so they will become dkx and dky. Now it should be more intuitive why we have this kind of integral, but what really matters here is that we have to integrate over kx and ky because they appear here and they affect the value for omega n. So we have to integrate over all those possible values. Now the problem with this expression here is that if you integrate, and remember that omega n as that expression there. So when we integrate over all the possible values for kx and ky from minus infinity to plus infinity, then the problem is that this is divergent, and it's quite easy to figure out from that expression there. It's divergent, and therefore we have to try to find a way to get rid of the infinity that we have. So what we are going to use is we are going to use a regulator, a so-called regulator. The regulator will serve to make the expression finite. And in the end, we will remove the regulator. Here, I want to use a different regulator than the one that I have used in a previous video. And in particular, we will rewrite the energy, the average energy divided by the area, like this. This is equal to h bar integral over dkx divided by 2 pi dky divided by 2 pi. Then I have summation over n from 1 to infinity. And here we have omega n, but we have to regulate this expression, otherwise it will diverge. Here we will put a decaying exponential of the kind e to the minus epsilon omega n, and as we let epsilon go to 0, you can see that we can restore the previous expression. So we will find some kind of divergences that will depend on epsilon. We will disregard those divergences and we will only consider the finite part of this integral here. And omega n, remember, is equal to c square root of kx squared plus ky squared plus n squared pi squared divided by a squared. So we can rewrite this expression like this. In particular, I can rewrite the summation here by means of a derivative to get rid of this omega n here. So we can write it as minus h bar d over d epsilon. Then here we have integral dkx dky divided by 2 pi squared summation over n from 1 to infinity e to the minus epsilon omega n, and now this can be written as minus h bar d over d epsilon summation over n from 1 to infinity integral dkx dky divided by 2 pi squared e to the minus epsilon times c square root of kx squared plus ky squared. Then we have plus n squared pi squared over a squared inside the square root. And now we're going to use polar coordinates. In polar coordinates, we can set kx equal to r cosine theta and ky equal to r sine theta. So this can be written as minus h bar d over d epsilon summation over n from 1 to infinity integral r dr d theta divided by 2 pi squared e to the minus epsilon c square root of r squared plus n squared pi squared over a squared, like this. Now we can integrate from 0 to 2 pi to get rid of this d theta here, and we will also be able to get rid of one of these 2 pi factors in the denominator. So here we have the following: minus h bar derivative with respect to epsilon summation over n from 1 to infinity integral from 0 to infinity dr times r divided by 2 pi. Let me write it properly. And then here I have e to the minus epsilon c square root of r squared plus n squared pi squared over a squared. So these are squares. Alright, now we can make a substitution inside our integral. In particular, we can set r squared equal to u, and from here we know that r dr is equal to du over 2. So this integral can be rewritten like this: minus h bar d over d epsilon summation over n from 1 to infinity integral from 0 to infinity. The integral is still from 0 to infinity du over 4 pi e to the minus epsilon c square root of u plus n squared pi squared over a squared. And now we can make another substitution. So the square root of u plus n squared pi squared over a squared is equal to v. So this is another substitution that we make, and if you wanted, you could have just skipped one step and made one single substitution. So you could have set this square root here equal to what we call v here, but never mind. If you just want to skip one step, it's okay. Anyway, this will become like this. So we have minus h bar d over d epsilon summation over n from 1 to infinity. Now the integral will start at n pi over a. You can easily check that, and we have to integrate all the way up to infinity. Then we have v dv divided by 2 pi, and this is because, of course, you can see it from here. So u plus n squared pi squared over a squared is equal to v squared. So the differential of u is equal to 2v dv, and that's how you do it, right? And then we have e to the minus epsilon c times v, like this. Now, this can be rewritten in this form, so you have minus h bar over 2 pi d over d epsilon summation over n from 1 to infinity minus 1 over epsilon c, which multiplies the integral n pi over a to infinity of v times the differential of e to the minus epsilon cv. So this factor here comes from the fact that you have put this decaying exponential inside the differential, right? So when you take the differential of this, you have to differentiate with respect to the variable v, and therefore you will get rid of that factor there. Now I have rewritten it in this form because we can integrate by parts. That's why I have done this. So this is equal to minus h bar over 2 pi, derivative with respect to epsilon. Then we have the summation over n from 1 to infinity minus 1 over epsilon c. Then here we have to evaluate v times e to the minus epsilon cv between n pi over a and infinity. And then we have to subtract the integral from pi n over a to infinity of e to the minus epsilon cv dv, like this. And this can be written as, of course, this is minus h bar over 2 pi d over d epsilon. Then we have summation over n from 1 to infinity. We still have the factor minus 1 over epsilon c. And then we have, so when you evaluate this at plus infinity, this will decay due to the presence of this decaying exponential. So you will only have to evaluate it at this other value. So we have minus n pi over a e to the minus epsilon c n pi over a, and then we have plus, then you have 1 over epsilon c, and we have to evaluate e to the minus epsilon cv between pi n over a and infinity. So when you integrate this term with a minus sign, you get 1 over epsilon c times this exponential, and then we can evaluate it between infinity and pi n over a. Simple as that. Now we can rewrite this as minus h bar over 2 pi d over d epsilon summation over n from 1 to infinity, and then we have 1 over epsilon c n pi over a e to the minus epsilon c n pi over a plus 1 over epsilon c squared, and then we are left with e to the minus epsilon c pi n over a, like this. Now we can rewrite this term in a more convenient way. In particular, I will rewrite it as minus 1 over c derivative with respect to epsilon of e to the minus epsilon c n pi over a, just like this, right? So just take a look at where we are going, because this will simplify what we have to do. In particular, I can rewrite my expression like this, so I can put this minus sign inside the parentheses, so I have h bar over 2 pi c squared that I can factor out from here and also here, and then I can rewrite the expression like this, d over d epsilon of 1 over epsilon d over d epsilon of the summation over n from 1 to infinity e to the minus epsilon c n pi over a minus derivative with respect to epsilon of 1 over epsilon squared summation over n from 1 to infinity e to the minus epsilon c n pi over a, like this. And now that you can check out the expression here, you can see that this term, this summation here, is exactly equivalent to this one. They are exactly the same. So we can just calculate one of them, and then the idea is to let, of course, epsilon go to 0. As epsilon goes to 0, we know that we will find some divergent terms, but we have to disregard those terms and only try to find the finite part. So I will discuss it more in detail in some minutes. But first, let's start from the summation that we have to calculate. Summation over n from 1 to infinity, e to the minus epsilon c pi over a, and then this is raised to the power n. So you can also rewrite this summation like this. But now this is a simple summation to carry out because it is a geometric series. So this is equal to 1 over 1 minus e to the minus epsilon, and now let me call c pi over a, just let me call it omega naught, omega 0, okay? So here we have omega 0, and then we have to subtract 1, because the summation starts at 1, so this is the result that we would get if the summation started at n equal to 0. But since it starts at n equal to 1, we have to subtract the value that this term has when n is equal to 0. But since the value that this term has at n equal to 0 is equal to 1, because something raised to the 0 is equal to 1, therefore here we have to subtract just 1. Now we can rewrite this as 1 divided by 1 minus. So if we expand this term in a series, we have 1 minus omega 0 epsilon plus omega 0 epsilon squared divided by 2, which would be a 2 factorial. Then we have minus omega 0 epsilon cubed divided by 3 factorial plus dot dot dot. You get the idea. And then we simply subtract 1. But now we can rewrite this. So let me rewrite it. You can simplify, basically you can simplify this, this 1 with this minus 1. So let me do it here for the sake of convenience. So here we can simplify it. We can simplify this 1, but we also have to change the sign here. We have to change the sign here and also here and so on. So here all the signs would change in this expression, but you can write it like this. Then we can also factor out of all these terms, we can factor out omega 0 epsilon. So I'm going to put omega 0 epsilon here, and of course the first term will become equal to plus 1. The second term, of course, we will get rid of this square. In the third term here, instead of a 3, we would get a 2. So this will be raised to the second power, not the third power anymore. Right? And now here you can see that we have this term is something like this. We have 1 over 1 minus x, where x is of course given by all these terms with a minus sign. So you can define x from here, but we know how to expand this. This could be expanded like this: 1 plus x squared plus x cubed plus dot dot dot. Okay, so you have more terms. And basically the idea, that same idea, we want to apply it to that. So here we have 1 over omega naught epsilon, and then we have 1 plus, we have omega 0 epsilon over 2 minus omega 0 epsilon squared divided by 3 factorial, And then you would have also other terms, possibly. We have to understand where to truncate it. But let me write another term. So we have omega 0 epsilon cubed divided by 4 factorial, if you understand the pattern, right? And dot dot dot. So you have other terms, right, that you can understand. So this subsequent term would be omega 0 epsilon to the fourth with a minus divided by 5 factorial, and so on, right? And then you have plus this term here squared. So you have omega 0 epsilon over 2 minus omega 0 epsilon squared divided by 3 factorial plus dot 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 squared plus dot dot dot. Then here I am left with a square bracket, and I have to subtract minus 1 from the expression. Now here comes the point where we in principle have to calculate all these terms, and there is an infinite amount of them, but we are going to focus only on the important terms. We will start from the terms in this expansion here inside the square brackets, which are proportional to epsilon to the fourth. So we are only going to consider terms which are proportional to epsilon to the fourth, because when they are divided by epsilon here, we are going to get something which is proportional to epsilon to the third power, right? And why are those terms important? Well, they are important because they give rise to the non-divergent part of this series. So we want to realize that. And for example, if you consider epsilon to the third, when you divide it by epsilon squared, you get something which is proportional to epsilon, and therefore when you take the derivative, you will get a constant from there. And similarly here, so if you replace something proportional to epsilon to the third power, when you take the derivative, you have something proportional to epsilon squared. And then when you divide by epsilon, you get something proportional to epsilon. And when you take the derivative, you get a constant. So the non-divergent part of the series, it's easy to realize that you will derive it by considering the term that is proportional to epsilon to the fourth from all these summations. So that's quite easy to realize. And now we are left with calculating that term. And after that, we will consider also the divergent part and also the other part that goes to zero. It will be quite easy to realize that. So we just have to do the calculation. Let's consider the summation that we started from. So we started from this summation here. And let me rewrite it in here. So we have the summation over n from 1 to infinity, e to the minus, and then we had epsilon c pi divided by a, which we call the omega naught, and this is raised to the power n, right? This is what we started from. And then here I'm going to consider only the part which is proportional to epsilon cubed, so it means that we are going to consider only epsilon to the fourth inside these square brackets. So try to follow me. It's not too complicated. When you divide by epsilon, you get something which is proportional to epsilon cubed. Now I'm using this symbol in this case just to consider the part which is proportional to epsilon cubed. So allow me to use this symbol. So it's not an equal sign because we also have other terms, but we are only interested at the moment in the part which is proportional to epsilon cubed. So we have this. We have 1 over omega 0 epsilon. So it's just, of course, this first term. And then, if you allow me to define all these summations here inside these parentheses as x. So this is x, this will be x squared, then you have x cubed, x to the fourth, and so on. So you have some contributions, so some contributions here, which are proportional to epsilon to the fourth. That's what we want. And the contributions are the following. So from the first term, which is just x, we get the term after this one. And what is that term? That term is minus omega 0 epsilon to the fourth divided by 5 factorial. This is the contribution of order epsilon to the fourth in the term which is proportional to x, right? That's quite easy. Then we get another contribution from x squared, and this will be slightly more complicated. We have, for example, we have omega 0 epsilon to the fourth divided by 36, and this one comes from the second term, because when you square this term, you get omega 0 epsilon squared, so we square it twice. It means that this is raised to the fourth power, and we divide it by 3 factorial squared, but 3 factorial is equal to 6, and when you get, so you have 6 squared, and of course that's 36. Plus, you also get another contribution from x squared, because if you think about it, you have twice, and then you have the product between this first term, which is just omega 0 epsilon divided by 2, which must be multiplied by the term that is proportional to epsilon cubed, and that is just omega 0 epsilon cubed divided by 4 factorial. So these are the only two terms that appear from x squared. Then you have another contribution from x cubed, if you think about it, right? From x cubed, you have 3 times the term which is, it is just this first term squared. So we have omega 0 epsilon over 2 squared. And then we have to multiply this by this term, the second one. So this is the only contribution that we have from x cubed, if you think about it, because all the other terms will be of higher order or of lower order, because if you take this one and you raise it to the third power, you get omega 0 cubed epsilon cubed divided by 8, 2 cubed. And similarly, so if you take the cube of this, you get something which is proportional to epsilon to the sixth power, because it's epsilon squared cubed. So it's epsilon to the sixth, and so on. So the only contribution that you get for the fourth order is 3 times omega 0 epsilon divided by 2 squared, and then you multiply this by minus omega 0 epsilon squared divided by 3 factorial. And finally, you only have one contribution from x to the fourth. This is very easy to see, because it will be just this term to the fourth power. And then here you have omega 0 epsilon to the fourth power divided by 16, and that's it. From here you get omega 0 epsilon, so you can factor it out. So you can factor out omega 0 epsilon to the fourth divided by omega 0 epsilon, so you get omega 0 epsilon to the third power, and then you have a bunch of terms, minus 1 over 5 factorial plus 1 over 36, and then you get plus 1 over 4 factorial, and then you get minus 3 divided by 4 times 6, and then you get plus 1 over 16. 1 over 16. And you just do the calculation. This is just algebra. You get minus 1 over 720 omega 0 epsilon cubed. And this is the calculation for the third order term. So it's the term of third order, because you get fourth order from the square bracket, and when you divide by epsilon, this is of third order. You have to replace it here and here. So you're going to get, on one side, you have to take the derivative with respect to epsilon. of 1 over epsilon squared of minus 1. So this is multiplied by minus 1 over 720. And then this multiplies omega 0 epsilon cubed. And this is going to give you minus omega 0 cubed divided by 720. Very simple, right? Because you get omega 0 cubed divided by omega 0 squared, which is just epsilon. So when you take the derivative, you're just going to get 1. So you get omega 0 minus omega 0 cubed divided by this constant, 720. And then you also have to take the derivative with respect to epsilon of 1 over epsilon, and then you have another derivative with respect to epsilon of minus 1 over 720 omega 0 epsilon cubed, and this is just minus omega 0 cubed divided by 720. You have to take the derivative of 1 over epsilon multiplied by 3 epsilon squared. So I have already taken the first derivative here. And then that's very simple. It's minus 3 omega 0 cubed divided by 720, like this. So basically, the energy here per unit area, E over A, is equal to h bar divided by 2 pi c squared. And then you have minus 3 omega 0 cubed divided by 720 plus omega 0 cubed divided by 720. And this is just going to give you, so remember that you also have other terms here, and we will say more about these terms. And this is just minus h bar divided by 720, and then you have omega 0 cubed. We also divide by pi c squared. So you have this term plus other terms, and we can rewrite it by substituting omega 0. So we know that we can rewrite this as minus h bar c cubed pi cubed divided by a cubed pi c squared 720 plus dot dot dot. And then finally, I mean, this is just a simple calculation. You get minus h bar c pi squared divided by 720 a cubed plus some other terms. So here you have a divergent part in particular. And we want to say something more about this divergent part. We will see that this part, this divergent part, will not be dependent on A. And it's important to highlight that the divergent part will not depend on A, because now we can calculate the force. So the force per unit area is just minus the derivative with respect to A of the energy per unit area. So we have to take this derivative and we have to put this minus sign. And I mean, this minus sign is important just because the force will be attractive. And here you get minus h bar c pi squared divided by 240 a to the fourth. So in this case, you don't have any divergent part here. The force is not divergent. Okay, so this is something that I want to highlight, and I want to say something more about this because I want to tell you how you can calculate this divergent part and show that it does not depend on A, which means that it will not depend on omega 0. So we have calculated the term that is proportional to omega cubed, and in particular we considered the term that was proportional to epsilon to the fourth here inside these square brackets. If we consider, for example, epsilon to the 5, epsilon to the 6th, so all terms that are of higher order here, then it's easy to understand that when you let epsilon go to 0, you will get something that's going to give you 0, right? So terms that are proportional to epsilon to the fourth or greater, because we saw that the non-divergent part comes from epsilon to the third power. So for example, if you consider epsilon to the fourth, you can see here that you get something proportional to epsilon squared if you divide epsilon to the fourth by epsilon squared here. So when you take the derivative, you still get something that's proportional to epsilon. And that's going to give you 0 when you let epsilon go to 0, right? And similarly here. So if you consider something proportional to epsilon to the fourth, here you get something proportional to epsilon to the third power when you take the derivative, something proportional to epsilon squared when you divide by epsilon, and something proportional to epsilon when you take this derivative. So all those terms that are of order epsilon to the fourth or higher order, they will give 0 contribution because they will go to 0. Whereas the divergent terms can be derived from epsilon squared, epsilon, and something proportional to 1 here, from here. And you might also have something proportional to epsilon to the minus 1 if you take a look at this, because you have 1 over omega 0 epsilon multiplied by 1 here. So we have to actually take into account the terms that are proportional to epsilon to the minus 1, 1, so this is epsilon to the 0. Then you have epsilon, and you get epsilon squared. We have to check what happens when we consider the terms that are proportional to this. So first, let's consider epsilon squared, right? If we consider epsilon squared, we want to rewrite this, these terms. In particular, we are only concerned with the terms that are proportional to epsilon squared there, which means that we have to consider terms that are proportional to epsilon cubed from here. It's easy to check. So let me rewrite it below. I'm going to consider the terms that are proportional to epsilon squared when we divide by omega 0 epsilon. So we have 1 over omega 0 epsilon, and then inside the square brackets, we are only interested in the terms that are proportional to epsilon cubed. So from the first term, that is x, so remember that we have a bunch of summations here. So we have x, which contains all these terms, and the first term that we have to consider is, of course, this one, because this is proportional to epsilon cubed. And let me write it below. So we have omega 0 epsilon cubed divided by 4 factorial plus, then you get another term, another contribution from x squared, which is minus omega 0 epsilon divided by 3 factorial, and then you get omega 0 epsilon squared, and this is the only term from x squared. So from x squared, if you take a look at x squared, the only contribution of order epsilon cubed comes from twice this term multiplied by this term, right? And then you get another contribution from x cubed, so it's just the cube of this first term. So it's quite simple. So here we have plus omega 0 epsilon cubed divided by 8. And if you do the calculation here, it's quite simple. You're going to get 0. So this will give no divergence, because this term is 0. So you don't have anything which comes from these terms. And it's very easy to check, because 1 over 4 factorial minus 1 over 3 factorial plus 1 over 8 is equal to 0. And it's quite simple, quite easy to check. This is 0. So we have checked the terms that are proportional to epsilon squared. Now we have to check the terms that are proportional to epsilon. It's going to be very easy, because now we have less terms. So terms which are proportional to epsilon, are the following. So we have 1 over omega 0 epsilon, and we have to consider terms that are proportional to epsilon squared inside the square brackets. We get 1 from x, and it's going to be minus omega 0 epsilon squared divided by 3 factorial. So it's very simple, very easy to check. It is just this term here. And then you get another contribution from x squared, so it is just the square of the second, so this term, omega 0 epsilon divided by 2. So you're going to get plus omega 0 epsilon squared divided by 4. And this term will give you omega 0 epsilon divided by 12. So this will give rise to the following. We have d over d epsilon of 1 over epsilon squared. Then you have omega 0 epsilon divided by 12. This gives minus omega 0 divided by 12 epsilon squared. And then you get another contribution from d over d epsilon, 1 over epsilon, d over d epsilon, omega 0 epsilon divided by 12. And this is just minus omega 0 divided by 12 epsilon squared. But now remember that we have to consider a subtraction. We have to take a subtraction and make a subtraction. Here we have a subtraction. So this term, the term that comes from here, will get subtracted from the term that comes from here. So when we consider these two terms, we have to subtract them, which means that we are going to get 0 because these terms are exactly the same. So we don't get any contribution of order epsilon. Now let's see what happens when we consider order 1. We are left with order 1, and then we also have to check order epsilon to the minus 1. Well, order 1 comes from the following. So we have 1 over omega 0 epsilon, and from the square brackets we only have omega 0 epsilon divided by 2. So this is the only first order contribution that we have inside the square brackets, because this is the only term that when we divide it by omega 0 epsilon is of order 1. Then we also have to remember to subtract this, we have to consider this minus 1 as well, because that's also of order 1. So here we get this minus 1, and this is just going to give you minus 1/2. So we have to take the derivative with respect to epsilon of 1 over epsilon squared times minus 1/2, and this is going to give you 1 over epsilon to the third power. And then you have d over d epsilon, 1 over epsilon, then you have a derivative of minus 1/2, which is a constant, and therefore from here we're going to get 0. Now, you have to notice that this will not give a term which is a function of a, because, you have a divergence from here, but this term does not depend on a, which means that it does not depend on omega 0. So this term does not depend on omega 0. So you will get a term that is proportional to 1 over epsilon cubed, and let me write it here. So this divergent part comes from what we just found. So we have a term that is 1 over epsilon cubed, and in particular, if we check, so this term is minus 1/2. When we divide it by epsilon squared and we take this derivative, it gives rise to this term. So in particular, if we check our expression, which is here, so this term appears in here. Then we have to consider this minus sign and multiply by this constant. So we have h bar divided by 2 pi c squared. We have h bar. Let me go back in in here. We have minus h bar divided by 2 pi h, sorry, c squared, and then we have 1 over epsilon cubed. This is the term. Remember that as epsilon goes to 0, this term will diverge. And when you take the derivative, though, since you are taking the derivative with respect to a, this divergent term will give you 0 contribution. So it will not appear in here. Finally, though, we still have to consider another term, which is epsilon to the minus 1. So we are going to get this term only from 1 over omega 0 epsilon multiplied by 1. Let's see if it gives rise to another divergence. And we don't want that to create any divergence. So this term here, which is proportional to, this is the term proportional to epsilon to the minus 1, should not give rise to any divergence, because otherwise, I mean, you can see that here we have omega 0. So if this term appears, we are in trouble, because it means that the force would be divergent as well. Because when we take the derivative, remember that omega 0 contains a, and therefore it will not give a 0 contribution when we take the derivative. So we would be left with a divergence also in the force. And we want this to disappear, according to what we said. Let's see if it actually disappears. Hopefully it does. So let's see. Remember that we have to take the derivative with respect to epsilon of 1 over epsilon squared, and then we have 1 over omega 0 epsilon. So this is going to give us minus 3 over omega 0 epsilon to the fourth when you take the derivative. Then we have another term. So we have derivative with respect to epsilon, 1 over epsilon, d over d epsilon of 1 over omega 0 epsilon. This is equal to minus derivative with respect to epsilon of 1 over omega 0 epsilon cubed. Here you're going to get 3 divided by omega 0 epsilon to the fourth. Now this is not good. This is not good at all, because you can see that these two, when you take the difference, because remember that you have to take the difference, you don't have to sum them. If you had to sum them, it would be great, because they would cancel. The problem is that we have to sum over them. We have to sum them. So we are not going to get 0. And this is quite bad. But let me tell you that there is a way to solve this. And I'm going to say something more about it. In particular, if we write down the average energy over the area, according to what we found the following. So minus h bar c pi squared divided by 720 a cubed minus h bar divided by 2 pi c squared epsilon cubed. And this term here is quite good, because when you take the derivative of this term with respect to a, this is going to give zero contribution, even if it diverges. Then we have another term coming from this result and also that one. So if you put them together, you have plus h bar divided by 2 pi c squared, and then you get 6 divided by c pi epsilon to the fourth, and then we multiply by a. So this comes from this term. Then you have to add the other one, because remember that you have to take the difference. So here, when you take the difference between this and this, you're going to get 6 divided by omega 0, 6 divided by omega 0 epsilon to the fourth, because we have to take this and then subtract this, if you recall from the expression that we derived above. And it is something that we have, where is it? Here. We did many calculations, so it was quite long, but in order to dig deeper, it was necessary, right? So this is what we found. So let me put together some terms. So this 6 divided by 2 will give us 3. I can put it here, but never mind. Then c times c squared will give us c cubed. And then we also have a pi squared. And I can cancel this pi. So you can rearrange it. It's not too difficult to rearrange it. The problem is that when we take the derivative with respect to a to find the force, this term will diverge as epsilon goes to 0. So in particular, you can see that this term is quite small because we have c cubed in the denominator, and we also have h, which is very small. So in general, if you don't consider epsilon to the fourth, you can see that it is different from this term here because you have c in the numerator, and then you have still h, but you have c in the numerator. So in general, this is much larger if epsilon is not too small. But epsilon will have to go to 0, if you recall, right? And this is the problem of our theory. The problem of our theory is that the physics behind the theory breaks at some point. And we have to be able to make sense out of what we have. Let me try to show you a possible way to remove this discontinuity. And a possible way to remove this discontinuity from the very beginning is that we could consider, instead of the two plates, so remember that we had the two plates like this. Now I'm just going to show you a sketch. We have the distance between the two plates, which is a. Let's assume that this is the z-axis. And we started from this, right? We imposed that the field here on this plate is equal to 0, and it should also be equal to the field on this other plate. But now we can put these plates inside a box, and you can think of this as a very long parallelepiped along the z-axis. So the length, the dimension over the z-axis of this parallelepiped is equal to L, and we assume that L is much larger than A, and you have to think that L goes to infinity. Okay? So we can resolve the issue if we make Z, the Z direction, periodic with this size L. Let me summarize what we did. Inside the two plates, we found that momentum K was discretized like this, kx, ky, and the third component was n pi divided by a. But actually, when we go outside, so when we consider the field out of the plates, k is discretized in a different manner, like this, kx, ky, and then we have n pi divided by L minus A, like this. Then, if we did all the calculation, but in this case using K equal to this, we would get something very similar to that, but the only difference is that instead of A, we have L minus A. That's the only difference. So in this case, let me call the energy in this second scenario, let's say in second case, E tilde average over A, and you're going to get exactly the same thing, minus h bar c pi squared divided by 720 L minus A cubed. And then we have minus h bar divided by 2 pi c squared epsilon cubed. And then we have plus h bar divided by pi squared c cubed. And then we have 3 L minus A divided by epsilon to the fourth. So what are we going to do with them? Well, the energy, the actual energy, let's call this E true, I don't know what to call it, E true divided by A, this is just the sum of what we previously called E over A. So this is the energy, you can think of this as the energy inside the two plates, and then we have the energy due to the contribution that we have outside. And now, since we let L go to infinity, remember, we don't have a contribution from this term due to the fact that the denominator goes to infinity. And what we get is minus h bar c pi squared divided by 720 a cubed minus h bar divided by pi c squared epsilon cubed plus 3h bar L divided by pi squared c cubed epsilon to the fourth, like this, right? And at the end of the day, you can see at this point that when you take the derivative with respect to A to calculate the force, the only contribution comes from this term. Contributions due to these terms are zero. So they will give zero contribution because they do not depend on A. In this case, you can see that here we have L. We don't have A anymore, right? So this is the size of the box. It goes to infinity, but when you take the derivative with respect to A, this will give zero contribution, and also this term here will give a zero contribution, like this.